Welcome to this explainer. Okay, let's jump right in. When you hear the name Albert Einstein, your brain probably goes straight to that classic, dusty black and white photo, right? The wild hair, the genius mathematician. But today, we're looking at him completely differently. We're going to explore how he wasn't just some historical figure. He was, quite literally, a time-traveling intellectual architect. Seriously, this is a guy who mapped out the absolute wildest invisible parts of the 21st century cosmos decades before the tech even existed to prove him right.
So how exactly did a guy born in 1879, way before we had orbiting satellites or supercomputers, build the entire framework for modern astrophysics using nothing but a pencil, some math, and his imagination? The crazy thing is, Einstein actually had a pretty ordinary early life. He even struggled in traditional schools just because he didn't fit that rigid mold of rote memorization. His mind just worked differently. He relied on collaborative debates and these highly visual thought experiments he called Gedanken experiments. Like he would literally just sit there and imagine, what would it actually look like if I was chasing a beam of light? He used this brilliant mix of raw imagination, intuition, and heavy math to completely rewire our understanding of reality.
Which brings us to our first major concept, el tejido del espacio-tiempo, or the fabric of space-time.
To really grasp how he maps the cosmos, we gotta start with his ultimate masterpiece, General Relativity, published back in 1915. Before this massive paradigm shift, the accepted science, Newtonian physics basically, treated space like a rigid stage, just an empty, unmoving box where stuff happened. And time was just a universal clock, ticking away at the exact same speed for everyone, everywhere. But Einstein, he looked at that rigid universe and just totally shattered it. He proposed this radical idea that space and time aren't separate, static things at all. Instead, they're permanently woven together into this single, flexible, four-dimensional fabric.
And that right there is the core of spazio-tempo, or space-time. To picture this, imagine a really huge, stretched-out trampoline. If you take a heavy bowling ball and drop it right in the dead center, what happens? It makes this deep dip in the fabric, right? Now, if you take a smaller ball and roll it across that trampoline, it doesn't just go in a straight line anymore. It circles and spirals down toward that heavy bowling ball. And here is the huge aha moment. That smaller ball isn't being pulled by some invisible magnetic force. It's just following the natural curve of the fabric. And that is exactly how Einstein explained gravity. Massive objects like stars and planets literally bend the physical fabric of spacetime around them, and smaller objects just follow along those curves. All right, moving into our next section, monstruosos cósmicos y ondas, or cosmic monsters and waves.
Because once you accept that space-time can bend like a trampoline, you logically gotta ask, well, what happens when it bends to the absolute extreme? In 1915, Einstein's math predicted that if a ton of mass got compressed into an infinitely small point, it would puncture and bend space-time so severely that absolutely nothing, not even light, could escape it. The historical irony here is just amazing. It was such a wild prediction that Einstein himself completely doubted it was a real physical thing. He just thought it was a quirk in his math. We didn't even get the term black hole until John Wheeler coined it in 1967, and we had to wait all the way until 2019 to actually get our very first direct image of one. It really makes you realize just how incredibly far ahead of the curve this guy's brain was.
Over a century later, our most advanced instruments are literally just now catching up to his pencil and paper. Take black holes. Recently, advanced X-ray telescopes actually caught light-bending echoes. We're talking literal X-rays coming from the far side of a black hole. The gravity is so immense, it bent those X-rays all the way around so we could see them on Earth, exactly like he said it would. And think about 2015, when the LIGO observatories detected gravitational waves for the first time. Try to picture two black holes violently crashing into each other in the dark universe. The impact is so massively powerful that it creates invisible splashes, actual ripples, in the fabric of spacetime itself. Those ripples travel for billions of years before finally washing over Earth and ever so slightly stretching and squeezing our planet. Just wow.
And those are just the start of the cosmic dances he predicted. Massive objects actually bend the light passing around them, acting like giant cosmic magnifying glasses, and something called gravitational lensing. When the alignment is just perfect, this creates these massive glowing Einstein rings out in deep space. We've also tracked stars tracing these wild, complex spirograph patterns as they tightly orbit supermassive black holes. Instead of a simple circle, they draw this beautiful, shifting rosette. Every single one of these mind-bending phenomena started purely in Einstein's imagination, decades before we ever had the telescopes to actually witness them. Now, I want you to consider the number 7. Why is that specific number such a big deal when proving Einstein right? Well, it represents 7 millimeters per day.
Back in 2003, researchers found a double pulsar system, basically two super-dense neutron stars orbiting each other. By throwing off gravitational waves, they lose energy and spiral closer and closer together. When scientists measured the exact rate that their orbit is shrinking, the answer was exactly 7 millimeters per day. That's the staggering, mind-blowing precision we're dealing with here. The actual, physical cosmos matches Einstein's century-old equations down to the literal millimeter.
Let's shift gears to Section 3. Luz, tiempo y cuántica. Light, time, and quantum mechanics.
So we've been looking at the massive, macroscopic scale of the cosmos. But Einstein's theories didn't just explain gravity. They totally rewrote the microscopic rules of atoms and light too. For instance, his foundational math showed that space itself could be expanding. That laid the total groundwork for Edwin Hubble to discover cosmological redshift in 1929. Redshift is kind of like the visual version of a siren dropping in pitch as an ambulance speeds past you. Basically, light from distant galaxies gets stretched out as space expands, which proved the universe started from a Big Bang. Plus, down in the weird quantum realm, his radical idea that the speed of light is constant eventually helped modern researchers prove that electron energy inside an atom stays remarkably constant too. But here's a beautifully ironic twist for you. Einstein actually strongly doubted the concept of quantum entanglement. That's the bizarre idea that two entangled particles can somehow instantly affect each other across vast distances of space, literally faster than light. He famously and very skeptically called this spooky action at a distance. In fact, to prove how absurd the idea was, he co-authored the 1935 EPR paradox paper to poke logical holes in quantum mechanics. And yet, that very paper brilliantly mapped out the exact mathematical framework that scientists used in 1982 to prove that this spooky action is 100% real. So even when he was completely skeptical and actively trying to prove a theory wrong, his genius still accidentally pushed science forward. Then there's his radical take on time itself. Einstein argued time isn't some steady river that flows identically for everyone. Instead, it's more like a flexible ocean. Literally, moving fast slows down time. To test this, it's called time dilation. Physicists Hafele and Keating did this incredible experiment in the 70s. They synced up these hyper-precise atomic clocks, strapped one onto a commercial airplane, flew it around the world, and then compared it to the clock left on the ground. And you know what? The flying clock ticked slightly slower. Time literally bent for it. And why does this matter to you? Well, because understanding this exact flexibility of time is absolutely crucial for keeping the GPS on your smartphone working accurately right now.
Which brings us to Section 4, Misterios y Advertencias, Mysteries and Warnings.
We're entering the final chapter of his work here, diving into the theories we are still desperately struggling to prove. First up, Einstein-Rosen bridges. You probably know them from pretty much every sci-fi movie ever as wormholes. Mathematically speaking, these theoretical shortcuts folding spacetime are entirely possible according to his equations. But, as physicists like Kip Thorne and Stephen Hawking have pointed out, these bridges would likely be microscopic and incredibly unstable, like they would instantly crush shut unless they were somehow propped open by hypothetical exotic matter. That's a mysterious substance with negative energy that repels instead of attracts. So yeah, for now, a quick shortcut across the galaxy is definitely staying out of our reach.
Then we have his great unfinished symphony, the unified field theory. This is basically the holy grail of modern physics. In his later years, Einstein desperately chased one single elegant equation that could link gravity, electromagnetism, and the strong and weak nuclear forces all together. And today, the physics community is still deeply and very neutrally divided on this. Supporters like Stephen Hawking and Brian Greene believe this beautiful, all-encompassing framework just has to exist out there in the math. But skeptics, like Lee Smolin, argue it might just be a conceptual leap without any real-world empirical backing. To this day, it remains one of the greatest, most fiercely debated open quests in all of science. But you know, perhaps his most startling prediction had absolutely nothing to do with physics. Einstein was profoundly concerned about humanity becoming overly reliant on technology at the expense of genuine human connection. He famously feared a day when technology would surpass our human interaction, leading to a disconnected generation. When you think about our modern world, navigating artificial intelligence, endless social media algorithms, the isolating metaverse, that prophetic warning just hits incredibly hard. It really shows how his intellect, his empathy, and his sheer observational power went far, far beyond just pure math and physics. Finally, we arrive at Section 5, El Legado Inmortal, the immortal legacy. As we wrap up this explainer, we really have to look at the incredibly strange events right after he passed. The scientific world's desire to understand his genius was so intense that when he died in 1955, a pathologist named Thomas Stoltz Harvey controversially extracted Einstein's brain for study, apparently without the family's initial consent. It is such a bizarre, almost grim historical footnote. Parts of his brain are actually still housed at Princeton today. But despite decades of slicing and studying and analyzing, the biological source of his monumental genius remains just as elusive and mysterious as the deep cosmic anomalies he theorized about. I want to leave you with this final, incredibly powerful thought from the architect of tomorrow himself. Information is not knowledge. The only source of knowledge is experience. He didn't just want us to sit in a classroom blindly memorizing his equations. He wanted us to actually experience, question, and boldly imagine the universe around us. And what does experience mean when we're talking about the vast cosmos? It means realizing we're all still just standing on the shore of this immense cosmic ocean that he helped discover. So what invisible mysteries are out there right now, just waiting for a new imagination to bring them into the light? Thanks so much for joining me on this explainer.